All right, let's finish up chapter 4 discussing yields. When we're talking yields, we are talking about how much we can make. And we're going to have three definitions. We're going to have theoretical, we're going to have actual, and we're going to have percent. Now, actual is if you go to the lab and you do the experiment and you actually collect a sample, how much you make is your actual yield. So this is from experiment. Theoretical is what you should make. So theoretical yield for any reaction is just the number of grams of product you should make. So when you do your stoichiometry, where you go from grams of a reactant into grams of the product, the number of grams of the product that you should make is inherently your theoretical yield. Your percent yield, by definition, is actual over theoretical times 100. And since there's no miracles in chemistry, your percent yield is always going to be less than 100. So let's just do this one. Theoretical yield. Theoretical yield is inherently the number of grams of product you should make. So you want to know how many grams of silver sulfate we're going to make. So the first thing we got to do is write the balanced reaction. So the balanced reaction is aqueous silver nitrate. Well, silver nitrate is AgNO3. Aqueous, all nitrates are soluble, so we know this dissolves. It's reacting with excess sodium sulfate. Now, excess just means we have enough of it, and we're going to ignore the amount. We'll deal with the details on that a bit later. It is going to make some silver sulfate, so we're going to have to do the formula correctly. Silver sulfate is Ag2SO4. We know from the solubility rules that that's going to be insoluble in a solid, and we're going to make two NaNO3s. And NaNO3 is aqueous. So remember, we write the molecular equation, which is what this is, to calculate how much. And we're looking for grams of our product. Our reaction is not balanced. We have two silvers on the product, so we're going to need two silvers on the reactants, and our reaction is balanced. Step 1, balanced reaction. Step 2, moles what we have. Well, we are given some silver nitrate. We know that volume in liters multiplied by the molarity is going to be moles. So we're going to put our volume in liters, take 50 and divide it by 1,000, and we're going to get 0.050 liters. We're going to multiply that by 0.35 moles per liter. That is going to give us a value here of 0.0175 mole of the silver nitrate. Now, we're going to use our balanced equation to get moles of what we need. Well, what we need is silver sulfate. And we know our relationship is 1 mole of silver sulfate for every 2 moles of silver nitrate, the 2 from our balanced equation. So we're going to divide that through by 2, and we're going to get 0.00875 mole of silver sulfate. We know that anytime we want to get mass, our mass is grams, and if we take moles and we multiply by molar mass, we're going to get grams. Molar mass of silver sulfate off the periodic table is 312 grams per mole, telling us that when we're done with this, we are going to collect 2.73 grams of silver sulfate. That is our theoretical yield. That is just grams of the product we should make. Now, the simple reality is when you mix things together, it's much more likely that one of the reactants is going to run out before the other. For example, you can run out of gas on the side of the road. You could also run out of oxygen on the side of the road if you're running your car, but it's a lot less likely. When you run out of gas, your car stops. And that is the key. When you run out of a reactant, which we're going to call the limiting reagent, the reaction stops and no more product is made. This reactant limits the amount, why it's called the limiting reactant or reagent. It gets completely consumed, and the stuff that is not completely consumed is called the reagent in excess, just meaning there's extra of it, and the amount of product that you can make from the limiting reagent is the theoretical yield. Now, this is the same as the theoretical yield before. This is just the amount of product that you can make. But if we have two different reagents that we know how much we have of, we're going to have to find the limiting reagent first, find the theoretical yield. So one way of looking at this, if Cheese sandwich is 2 slices of bread and 1 slice of cheese, and we're given 28 slices of bread and 11 slices of cheese. We know that we're going to be able to make 11 sandwiches, and if we take our bread, and we need 11 of those, so therefore we're going to use 22 slices of bread. This is going to limit how much we're going to make. Our cheese is our limiting reagent, and our bread is in excess. As soon as we run out of cheese, we stop making sandwiches, and we're going to have 6 slices of bread left over. Equally, we could have hydrogen reacting with chlorine. Now, the reaction from hydrogen to chloride to make HCl is 1 to 1. So each hydrogen reacts with a chlorine to make 2 HCl. Now, we have 6 moles of hydrogen and 4 moles of chlorine, or molecules in this case. If we need 1 to 1, we know we're going to have 2 of the hydrogens left over. And our reaction is going to stop when we run out of our chlorine. Our chlorine is our limiting reagent. Our hydrogen is in excess. The best way to do this is to simply do this. And let's do a practice problem. Our logic is not changing. Our step 1 is balance. Our step 2 is moles of what we have going into moles of what we need and finishing the equation. Except instead, we're going to have 2 different compounds that are going to provide us with moles. So we're going to do each. We're going to take 124 grams of aluminum. We know the molar mass of the aluminum is 1 mole of aluminum for every 27 grams of it. And I'm going to combine this just to save space. We're looking at this product. We could look at either product, but we're choosing to look at aluminum oxide. And we know there's 1 mole of aluminum oxide for every 2 moles of aluminum. And if we continue this, we can find the molar mass of aluminum oxide. Aluminum oxide weighs 102 grams per mole, and that is going to give us a total of 234 grams of aluminum. Now, that's the yield starting, or aluminum oxide, excuse me. That's the yield of aluminum oxide starting with aluminum. But we have 2 reagents. We have to figure out which one is going to run out first. So we're going to do the same problem, but instead of starting with aluminum, we're going to start out with the iron-free oxide. And when we do this, we're going to get the molar mass of iron oxide, and the molar mass of this is 1 mole for every 159.7 grams. We know that there's 1 mole of the aluminum oxide for every 1 mole of the iron oxide. And we're going to use the molar mass of aluminum oxide, 102 grams per mole. We're calculating the same product both times so we can do a direct comparison. And that's going to give us 384 grams of aluminum oxide. We cannot get both of these. The reaction stops when I run out of something, and it stops when I run out of the smallest. So the smallest value of the product is going to come from the limiting reagent. So the limiting reagent is aluminum, and the mass of aluminum oxide formed is going to be 234 grams. We are going to ignore the other value because the reaction stops as soon as the aluminum runs out. All right, so we've done the math and we know that aluminum is limiting and that we are going to make from our limiting reagent 234 grams. And we are always going to calculate the theoretical yield, which again is just a mass of product formed from the limiting reagent. Whatever you run out first, because the reaction will stop as soon as you run out of the one that is the limiting. So what does this tell us? Well, this tells us that iron oxide is left over. Question is how much? Well, we can do this as well. We know that we start with 601 grams of iron oxide. If we can calculate the number of grams of iron oxide that react, and we can subtract that, we're going to get the grams of iron oxide left over. And the key with all of these problems is we always go back to the limiting reagent because it's going to tell us how much of the other thing we need or how much product it's going to make. So we're going to go back to 124 grams of aluminum. And we're going to do the same thing, except we're going to end up with the iron oxide. We know there's 1 mole of aluminum for every 27 grams of it. We know there's 1 mole of iron oxide for every 2 moles of aluminum from our balanced reaction. And we know from the periodic table there's 159.7 grams of iron oxide per mole of the molar mass. And that is going to give us a total of 368 grams of iron oxide reacted. So left over is going to equal 601 grams, which is what we started with, minus 368, which is what reacted, to give us left over 234 grams of iron oxide. So theoretical yield is the amount of product that you would make. It would be assuming that all of whatever is limiting would react. We've always made that assumption. The actual yield is the amount of product that you obtain from the reaction. And again, this is in the lab. You can only have an actual yield when you do the experiment in the lab. So let's do this one. We want to know how much hydrofluoric acid we can make from the reaction of 75 grams of sulfuric acid with 63 grams of calcium fluoride. Step 1, balance the equation. 2 fluorines on the reactants, so I need 2 on the products, and the equation is balanced. Moles of what we have. Well, we have to consistently start and calculate the moles from the grams of each of these 2 reactants. So we're going to start out with 75 grams of sulfuric acid. We're also going to do 63 grams of calcium fluoride, and we're going to calculate how much HF, only because that's what they're asking us for, we can make from each of these 2. The one that is smallest comes from the limiting reagent. So our molar masses from the periodic table, 1 mole of sulfuric acid for every 98 grams of sulfuric acid. Looking at our relationship, we have 2 moles of hydrofluoric acid for every 1 mole of sulfuric acid. And our molar mass of hydrofluoric acid is 20 grams per mole. And that is going to give us, starting with the sulfuric acid, a total amount of 30.6 grams of HF. We're going to do the same calculation with calcium fluoride. 1 mole of calcium fluoride for every 78 grams of calcium fluoride. Relationship is 2 moles of HF. Again, from the balanced equation, for every 1 mole of calcium fluoride, molar mass of HF is 20 grams per mole. And from the calcium fluoride, we could make a total of 32.3 grams. Now, we know that we're going to ignore the one that gives us more. The correct answer comes from the one that gives us a smaller amount. And we know that H2SO4 is limiting, and that we're going to make 30.6 grams of HF. So the last couple of steps, we're going to figure out how much of the calcium fluoride we have left over, and we're going to do a percent yield. So let's do this one first, just because it's easier. If the actual yield is 26.2, what is the percent yield? We know that the theoretical yield for this reaction was 30.6 grams. Our percent yield by definition is actual over theoretical times 100. So we're going to take our 26.2 divided by 30.6. We're going to multiply by 100, and we are going to get a percent yield of 85.6% yield. Now, how many grams of the calcium fluoride are going to remain? So we know that this is going to be what we start with, which is our 63 grams, minus the number of grams of calcium fluoride that react, and that's going to give us the grams of calcium fluoride left over. So we have to go back to the limiting reagent in all of these cases. So back to our limiting reagent is our 75 grams of sulfuric acid. And straight through the same process we've done before, 1 mole for every 98 grams. We have 1 mole of calcium fluoride. For every 1 mole of sulfuric acid, always go back to the balanced equation for the mole ratio, multiply by the molar mass of calcium fluoride, 78.1 grams of calcium fluoride per mole, is going to give us a total here of 59.8. This is the number of grams of calcium fluoride that react. We know, therefore, that what's going to be left over is 63 minus 59.8, and we're going to get a total of 3.2 grams of calcium fluoride left.